All right, welcome in. This is our second lecture for Chapter 1, talking about organic chemistry. In this lesson, we will continue our discussion. We were thinking about, just a quick overview of organic chemistry. Today, we're going to focus on key functional groups in our organic molecules. These common repeating patterns that show up again and again, and that can help dictate some of these organic molecules' properties. All right, so our first functional group are going to be alcohol groups or hydroxyl groups. These alcohol groups are these OH groups that we've seen in our previous video. This is an OH attached somewhere to our carbon chain. These alcohol groups, these OH groups, these hydroxyl groups, they can, as we said, dictate some of the properties. If we have an oxygen attached to a hydrogen, like we have in this molecule down below, well, this hydrogen can exhibit hydrogen bonding, and it can look for an oxygen in a neighboring molecule. So, okay, when we have hydrogen bonding, this is a specific intermolecular force in our molecule, which will dictate the physical properties. Alcohols will tend to have maybe higher boiling points, higher melting points. Chemistry. This is our last class of compounds for our class, where we're going to introduce the nomenclature rules in detail and think about how to name these molecules. So for our alcohols, we want to indicate, well, that it's an alcohol, and so we'll change the ending of our name. Instead of the ending for alkenes or alkanes or alkynes, we're going to change the ending to OL. We are also going to indicate where that hydroxyl group is in our molecule. And so we can use an infix. We'll have a number right before that OL ending. If we have multiple alcohols in the same molecule, we can indicate that as well. But we're going to try to keep it at least a little bit simple for our examples. If we want to draw some of these simple examples, we can have maybe one carbon with this hydroxyl group. This would be, well, the root name for one carbon is meth. Instead of methane, we're going to call this methanol. That OL ending denoting that we have an alcohol. We have a quick practice problem here, thinking about the properties of our molecules. What do we expect to have a higher boiling point, propane or propan-1-ol? Ooh, well, let's draw these molecules here. Propane is going to be 1, 2, 3 carbons. Propanol is going to be 1, 2, 3 carbons, but we have an OH group on our first carbon. So here's 1 carbon, 2 carbons, 3 carbons. That is the prop. If we have just propane, this is 3 carbons, nothing attached to it. We have propan-1-ol. That means, well, our first carbon, 1, 2, 3, our first carbon has that hydroxyl group attached. And you can write this as HO or OH. Both are fine with me. If you want to include the lone pairs, there are going to be lone pairs on that oxygen. That's what we get. Now we can answer this actual question. which will have a higher boiling point? Well, the one that has stronger intermolecular forces looks like it's going to be the alcohol. All right, moving on to our second functional group, we can have ethers. We can have oxygen in our organic molecules, but not as something sticking off the end or off the side. We can have oxygen as part of the chain, as a bridging atom. When we have this bridging oxygen, we call it this an ether. We can abbreviate this. Well, R represents a string of carbons. A string of carbons attached to an oxygen attached to a different string of carbons. This is an ether. Or looking at our examples down below, we can have a ethyl group attached to this oxygen, attached to another ethyl group. We're not going to focus too hard on the naming rules here in our course. You might see this written as, well, naming what are attached to that oxygen. Diethyl ether will describe this molecule. Or we can have a more formal name using the IUPAC rules with the alkoxy naming system for some of our groups. Either is okay with me, and we don't need to focus on exactly how to do this, but we do want to think about, well, what are the implications of this ether group? Can we recognize ethers when we see them? When we have ethers, well, we have some polar bonds. These are going to be maybe just very slightly polar molecules that do not exhibit hydrogen bonding. So ethers more likely to be volatile, more likely to be gases than things like alcohol. All right, moving ahead, we can look at a few different types of carbonyl groups. Carbonyls are when we have an oxygen sticking off of our carbon chain, and this oxygen is double bonded to our carbon. This C double bond oxygen. Depending what's on either side of that carbon, we can have a few different types of organic compounds that all contain this carbonyl group. We might have aldehydes, ketones, carboxylic acids, esters, or there's even other ones once you start adding other types of elements. But here are the ones that we'll actually look at for a moment: aldehydes, ketones, carboxylic acids, and esters. All right, aldehydes, they have this carbonyl group, and attached to that C double bond O is going to be, well, a carbon chain on one side and a hydrogen on the other side. We have it circled here. There's the carbonyl C double bond O, and one side of this contains just a hydrogen. Here's another example, C double bond O, that's the carbonyl. Since there is a hydrogen next door, this is also an aldehyde. Or if you want to see the Lewis structure, here's a simple aldehyde, C double bond O. One of these is a hydrogen, one of them is a carbon chain. Aldehydes here, they tend to be very aromatic compounds, very in terms of smells and scents. Some of the flavor and aroma components for like vanilla and cinnamon are molecules that contain these aldehydes. Our next option for carbonyl containing groups, carbonyl containing molecules, are ketones. Ketones, we still have that C double bond O in our molecule, but now on both sides of that carbon are more carbons. Here's that carbonyl. On one side is a carbon group, on the other side is a carbon group. This is a ketone. A subtle difference between ketones and aldehydes. We have the nomenclature rules written up here. Again, we're not going to focus on this for our course, but have fun moving forward in future organic chemistry courses, learning all the different naming rules for all the different types of compounds. Once again, with our ketones, they tend to be molecules that have intense smells or flavors. This is what cloves or spearmint, some of the molecules here that make those distinctive smells contain these ketone functional groups. As promised, we want to introduce a few different types of organic reactions when we have aldehydes and when we have ketones. Well, these carbons in our carbonyl group is going to be extra reactive. Our carbon, when it's double bonded to an oxygen, well, it's part of this polar bond. And so the oxygen is more electronegative. It will pull the electrons away from that carbon, leaving our carbon looking for extra electrons. We can have some electron-rich molecules come in, donate some electron lone pairs, and form a new bond to our carbon in that carbonyl. This is an example of Lewis acid, Lewis base chemistry. Lewis acids are going to be electron pair acceptors. Lewis bases are electron pair donors. And instead of, well, just giving these electrons away, they're going to share them by forming a new bond. And so our result is going to be, well, our carbon is attached to that oxygen, attached to that R group, attached to that other R group. And now this X that has come in is going to form a bond here as well. And as those electrons come in and form a bond, maybe some of these other electrons get pushed around. Maybe we end up with a slightly negative molecule because we've added some lone pairs here. But we can form a new bond between our carbon and this incoming molecule. All right. Two more types of carbonyl containing functional groups. Our second to last is esters. Esters have this carbonyl. On one side is a carbon. On the other side is an oxygen attached to more carbons. So it's almost like we have maybe an ether with that carbonyl right next to that other oxygen. Right, so the carbonyl, one side is a carbon, the other side is a bridging oxygen. Once again, we have, well, polar bonds and we have no hydrogen bonding. So our esters, again, have their properties dictated by these types of things. We have the nomenclature rules here just in case we see some of these names out in the wild. Again, not going to be a large focus for our course. And in fact, we'll see many common names for the simple esters. All right, our last carbonyl functional group are going to be carboxylic acids. Carboxylic acids contain, well, that carbonyl group, carbon double bonded to oxygen. One side is going to contain another carbon, and the last bond is going to be an OH group. So we have that carbonyl and then attached to an OH group on one side. We like to abbreviate this COOH. This is a common thing that shows up. Carboxylic acid groups, as the name implies, are going to be acidic. This hydrogen, different than our alcohol group, this hydrogen is going to be acidic, is going to be able to pop off in our solutions. The reason for that, well, we get to have some resonance once that hydrogen is gone. We're going to stabilize the conjugate base of these carboxylic acids using resonance. All right, and finally, Our last functional group is going to be this amine group. These are related to ammonia. Ammonia, of course, being our NH3 molecule. These amines are going to start to replace some of those hydrogens in our ammonia molecule, replacing some of those hydrogens with carbon groups, with carbon chains. So we can start to have, well, maybe one carbon chain or two carbon chains or up to 3 or 4 carbon chains attached to those nitrogen atoms. We can call these primary amines if we just have one carbon group attached. Secondary amines if we have 2 carbon groups attached. Or tertiary means 3. Tertiary amines have 3 carbon groups attached. When we have nitrogen, nitrogen is going to have, well, probably 3 bonds in a lone pair. That lone pair can be reactive. It can act as a Lewis base and be donated away when we react with other molecules. Since we have these lone pairs, since this molecule can be a Lewis base, our amine molecules are going to be weakly basic. These are going to be weak base molecules. In biochemistry, we can start to react acids and bases. In fact, we can react our amine molecules with our carboxylic acid molecules and form, well, bigger molecules. Amino acids are going to contain both an amine group and a carboxylic acid group, which means the amine group on one side can react with the carbonyl group on another side. We can start to link these amino acids together, start to form chains of amino acid molecules, which are known as peptides or proteins. In biology, these proteins get to fold up into secondary and tertiary and quaternary structures, which end up allowing them to function as, well, parts of our cells and our bodies. An interesting thing here, once we have these carbons surrounded by maybe 4 unique bonds, 4 unique groups on our single tetrahedral carbon in the middle, well, we can start to introduce a new type of isomers. These are known as stereoisomers or optical isomers. Stereoisomers, well, they're isomers that have the same chemical formulas, but different arrangements in space. And these stereoisomers, in fact, they are mirror images of each other that are non-superimposable. Mirror images that are different from each other. Like we said, when we have a tetrahedral carbon with 4 unique atoms attached to it, 4 unique groups attached to it, these will form stereoisomers. These will form optical isomers. Here we have a tetrahedral carbon and its mirror image. If we look at these 2 molecules, there's no way you can twist them around to be the same thing, to be superimposable, to put them on top of each other. This is the same thing as your left hand and your right hand. Look at your left hand, look at your right hand. They are mirror images of each other. Can you twist your left hand upside down, backwards, a different way to be another right hand? Well, no, your left hand and your right hand are different things. We call this handedness. Your hands are optical isomers. These tetrahedral carbons are also optical isomers. We'll have a chance in our lab to play around with some modeling kits, build some of these molecules and look at this ourselves. But that is our idea for optical isomers. Molecules that have the same chemical formula, the same connectivity, but when you take the mirror image of one, it is different from the other mirror image. All right, and that brings us to the end of our discussion on different functional groups. Once again, we want to be able to identify these functional groups, understand some of the relative properties of these molecules, and at least for alkanes, alkenes, alkynes, and alcohols, be able to name molecules or draw molecules given the name. I hope this has been helpful. If you have any questions, feel free to reach out, and I look forward to seeing you in the next video. Thank you so much, and have a great day.